Hey guys, thanks for tuning in. In this video, we are going to talk about how to use gradient vectors to classify local extrema on surfaces living in 3D. So basically, if you have an equation for a surface, where are those candidates where you might have local maxes or mins on your surface? Where do you have little mountain peaks, and where do you have the lowest points on a valley? And so what I'm going to start with is we're going to use our definition for the gradient vector to try to rewrite the equation for a tangent plane, because you guys are already familiar with this equation. This is the equation for a tangent plane. I wrote it in terms of the linearization equation, but let me get my ink going here. So you guys are more familiar with that L of xy being a z equals, but the language that you're going to see throughout this chapter starts to use this L of xy linearization, a tangent plane being a linearization of a surface at that point of tangency. And anyway, what I'm going to do with that equation is I'm going to look at the portion that has the partial derivative of f with respect to x and the other part that has the partial derivative of f with respect to y. And I'm going to extract those out using a dot product. So I've got f partial x comma f partial y dotted with x minus x naught comma y minus y naught. So just using the properties of the dot product to separate those two pieces. And then what that allows us to do is we can see that the equation for a tangent plane actually has the gradient vector involved with it, and we're going to use that in the coming slides. So we're going to do our first example here. First, we're going to compute the gradient vector for an equation for a surface that's given right here. F of xy is equal to x cubed plus y cubed minus 3x minus 3y. That's plotted right here. And the problem says to find candidates for where f of xy could have a local maximum or a local minimum. And you can already see in the animation where this is going. This might be reminiscent of when you guys took Calc BC and you were looking for the places where you had candidates for local maxes and local mins on curves. And where did those candidates live? It was exactly where you had horizontal tangent lines to your curve. Something like that. And same thing is going to happen with a surface. Our candidates for local maxes and mins are places where we have horizontal tangent planes. Now I picked this surface carefully because you could see there are places where we have candidates where they are neither maxes nor mins. Same thing happened in Calc BC, but we want to make sure we're aware of this as well in multivariable calculus. Just because you have a candidate doesn't mean it's necessarily a local max or min. You have to do more investigation. So anyway, let's follow the instructions here. So first we're supposed to find the gradient of f, which is just a vector made up of partial derivatives. So I'm going to take my equation, x cubed plus y cubed minus 3x minus 3y. I'm going to take its partial derivative with respect to x. Now those y values are going to get knocked out because they are constant relative to x. And so I really just have the partial derivative of x cubed with respect to x, which is 3x squared, and the partial derivative of negative 3x with respect to x, which is negative 3. Same idea when I take my original equation for my surface and take partial derivatives with respect to y. My second component of the gradient vector here is 3y squared minus 3. Now, remember that just like in Calc BC that we have candidates for local extrema where we have a horizontal tangent line, in this case we need to figure out where z equals f of xy has candidates for local extremes where the surface has a horizontal tangent plane, just like I was showing you in the animated GIF. And the other thing to remember is on the previous slide, I had rewritten my linearization equation as the gradient of f evaluated at our point of tangency x naught y naught dotted with x minus x naught comma y minus y naught plus f of x naught y naught. Anyway, the place where I have a horizontal tangent plane is precisely where the slope in the x direction is 0 and the slope in the y direction is 0. That's where I'd have a horizontal tangent plane, or where the gradient of f is equal to 0, 0. That kind of makes sense because the equation of one of these planes, a horizontal plane's equation would just be like z equals, I don't know, it looks like it's about 4, right? Z equals some constant. And how am I going to turn my linearization equation, this big complicated equation, into z equals a constant? Well, I would need this entire section of the equation to zero out, i.e. I would need the gradient of f to be 0, 0, so when I dotted everything out, it just got zeroed out, and all I'm left with is that z value. So anyway, what I'm going to do is I'm going to take my equation for my gradient, which in this case is the vector 3x squared minus 3 comma 3y squared minus 3, and I'm going to set it equal to 0, 0. I'm going to solve those two equations. So I'm going to thread this out. My x component equation turns into 3x squared minus 3 equals 0. The y component turns into an equation of 3y squared minus 3 equals 0. And I'm going to solve each of them. I'm not going to show you the steps. It just gets, you get x equals plus or minus 1, y equals plus or minus 1, and then if we put this together into ordered pairs, we have 4 candidates. We might have a local maximum or minimum or neither, but our candidates for maxes and mins are at x equals 1, y equals 1, 1, negative 1, negative 1, 1, and negative 1, negative 1. And if you look at the animated GIF, you could see that there are 4 places where our surface has horizontal tangent planes, and those are going to correspond with those 4 candidates that we just found. So in general, here's how you do this. So I have a little theorem here for a function of n variables, for a differentiable function of n variables. The candidates for local maxes and mins are the places where the gradient of f equals the 0 vector. And this is analogous to being in Calc BC and saying that the places where a function y equals f of x might have a local max or min, the candidates for maxes and mins on a curve f of x are the places where f prime of x is equal to 0. Also the places where it's undefined, which is also technically true here, but I'm skirting around that by saying I have a differentiable function. Some of those edge cases that you guys are familiar with from Calc BC kind of fall away in a multi-class. Not that they don't exist, but there's less emphasis on them just because the math is hard enough just for the differentiable case. So in any case, for this course, you really only need to worry about when the gradient vector is equal to the 0 vector, which is analogous to when the derivative is equal to 0. But now we're setting equal to a vector of zeros, the 0 vector. Again, these points are just candidates. They're places where the tangent plane to the surface is horizontal. That's what we're finding. But the places where the tangent plane to the surface is horizontal are also the places where you might have a max or a min. So those are our candidates. We have to do more investigation to actually classify. So on this slide, what you could see is I'm continuing with the same exact example. I've got my candidates at x equals 1, y equals 1, the 1, negative 1, negative 1, 1, negative 1, negative 1. And one way of classifying would be to use those 2D plots that we learned about in the previous lecture. So you could use a contour plot, like you see here. You could use a gradient vector field, like you see here. And that can be an effective way to classify your critical points. Now, it kind of requires you to have a computer or a lot of time to draw the plot, but we could see that here we have, this is our highest point. It's kind of like the highest altitude point on this island. This is our lowest point, our minimum. And then the places where your level curves cross, that's called a saddle point. You saw it on the previous slide. Basically, the curve goes up in some directions and down in others. So it's neither a max nor a min. And you can recognize it because these level curves cross each other. Or you could recognize it in the gradient vector field because some of these gradient vectors are flowing in and some of them are flowing out. So uphill in some directions, downhill in others. And so saddle points are neither maxes nor mins. There is a critical point at these saddle points. They're interesting, but they're neither the local max nor min. So this is one way to classify our local maxes and mins. A local max, again, if you're looking at the gradient vector field, you would look at all of the vectors in a neighborhood of your critical point flowing into that point. Or for a local minimum, like right here, all of your compass readings, all of your vector gradient vectors are flowing out in a neighborhood around that point. So you could use these 2D plots to classify. It's not necessarily feasible to do this in every problem because you may not have that information available. Like you might not have a contour plot, and it's not feasible you don't have a computer in front of you because you're taking a quiz, and you're not given a contour plot. In that case, it's not really feasible to spend time drawing one because it's time consuming. So we need a better way, but this is a good start. So here's just a nice summary of everything. We've got all three pictures together, and really the end point here is you should be able to look at any of these three plots and make sense of what's happening. How to, classifying your maxes and mins in all three of these different variations of the same information. So I said we need a better way, so let's come up with that better way. So previously we needed a contour plot with a bunch of level curves, or we needed a gradient vector field to classify our maxes and mins. What we're going to do now is we're going to take the second derivative test that you're familiar with from Calc BC, and we're going to kind of lift it up to multivariable calculus. So you can kind of already see what's going on in my picture. I think the animated GIF already kind of shows what's happening. We need to look at the concavity of our surface, the second derivative, in a sense, of our surface at a given point, and use that to try to figure out if we have a max or a min. So just like in Calc BC, if you had a curve with a critical point, say right here, and so you checked the first derivative and you saw that it was 0, so you have a horizontal tangent line, and then you tested the second derivative and saw that it was concave down, that was a maximum. And we have an analogous situation with the green point on our animated GIF here. If we're concave down in all directions at that critical point, again, we're going to have a maximum. So how do we detect that? So anyway, at the point 1, 1, the surface is concave up in all directions, so we think that's a minimum. The green one, concave down in all directions, maximum. And then if we have disagreement between those concavities, sometimes concave up, sometimes concave down, that's going to be one of those saddle points where it's neither a max nor a min. So we can kind of see we need a technique for detecting this concavity. And we need that concavity to be detected in all directions. It's not enough to just take one slice of our surface and say, oh, we're concave up in this slice, and so therefore we have a minimum. No, we need to look at all 360 degrees of concavity that we could have. So to try to detect that, we have a second derivative test, and it uses an extra piece of information called the Hessian determinant. The Hessian determinant, this is something you need to memorize. You could see it's built out of second derivatives. And so proving exactly why this works and that this works is a little more complicated than we're able to go in with this course. But what I want you to see is this Hessian determinant is a 2x2 matrix made out of second derivatives. The thing is, there's a lot of second derivatives that you could take, second partial derivatives, but there's a lot of second partial derivatives you can take in a multi-course, because you could take your function f of xy, and you could take its partial derivative with respect to x, and then you could take its partial derivative with respect to x again, and that's one way to try to describe the second derivative, and that's what you see in this first entry. Or you could take your f of xy and take its partial derivative first with respect to y, and then again with respect to x. Actually, I don't remember the right order to write that in, because I don't use this notation very often, but I think that matches up there. But either way, the idea being there's a lot of different ways to describe a second derivative in a multivariable calculus course. And so this matrix has 4 different second derivatives. And you take the determinant of that matrix, and here's what this determinant is going to tell you. When you take the determinant at your critical point, if that determinant is positive, what it's going to tell you is the concavities agree. The concavity in the x direction and the concavity in the y direction agree. So I'm going to say concavity in x and y direction, and all the directions in between. They're going to agree with each other, which tells you you either have a max or a min. Now, if you wanted to figure out which one it was, is it a maximum or is it a minimum? All you need to do is then now pick, a slice in a second derivative in one direction, and because we have agreement, that'll determine all directions. So what we do is we look at the second derivative with respect to x, which happens to be this entry from the matrix anyway. So you kind of take this guy right here, and if it's negative, well, negative would be concave down. Concave down aligns with a maximum. Or likewise, you can look at that second derivative with respect to x, again, this entry right here, and when it's positive, that would be concave up, and that would be a minimum. And then the other thing that could happen is that your Hessian determinant evaluated at your critical point could come out to negative. And if it's negative, that means we have disagreement between our concavities. The concavity in the x direction and the concavity in the y direction disagree with each other. That's what that's telling you. In that case, we don't need to worry about any more investigation. We have disagreement in our concavities. We have a saddle point. And then it is always possible for that determinant to come out to 0. In that case, the second derivative test is inconclusive, which also happens in Calc BC. You did get second derivatives equal to 0, and then in that case, you'd have to just do something else. Like on a triad problem, you'd probably just plot a contour plot or a gradient vector field and use that to determine what was going on. So that is how we use the Hessian determinant. So let's keep on rolling here. So here is the equation for the Hessian determinant again, and I can kind of just summarize that information. Again, when that determinant is positive, the concavity is pointing the same way in all directions. It's indicating agreement amongst our concavities. Might be concave up in all directions, might be concave down in all directions, but it's telling us we have agreement in the concavity. So then, at that point, all you have to do is distinguish between a max or a min by looking at one of your second derivatives, with the top left entry of the matrix being the fastest one to find. Also, taking derivatives with respect to x is what you're most comfortable with. So that first top left entry is probably the best one to look at for being positive or negative, because it kind of, you guys are so used to taking derivatives with respect to x anyway from being in Calc BC. So again, if that second derivative with respect to x is negative, you got a max. Positive, you got a min. And then when that determinant is negative, the concavity points in different directions, saddle point. So let's actually do this with the problem we were working on. So remember, we had 4 critical points, 1, 1, 1, negative 1, so on and so forth. So let me walk you through the calculation here. So you can see I unpacked what this notation means, because this says the second partial derivative of f with respect to x. So this notation is the same as saying I'm taking my f of xy and I'm taking its partial derivative with respect to x. Sorry, let me grab the eraser. I just put an extra f in here by accident. Let me get the pen back. Okay, so I'm taking my function f of xy and I'm partial ddxing it once. So I'm taking f and taking its partial derivative with respect to x once, and then I'm taking its partial derivative with respect to x twice. That's where the square comes from. You could kind of think of this as being d times d is d squared, and you could kind of think of dx times dx as dx squared. Anyway, that's what you see right here. So really, this differential, this partial differential, is just, it's kind of like an action word. It's telling you, take the partial derivative with respect to x. And the function in this case is this x cubed plus y cubed minus 3x minus 3y. And so I unpacked all 4 of these. You could see all 4 of them. And so you just resolve these from inside out. So I'm going to do the inner one first for each of these. Now you'll notice these are just the components of the gradient. We already computed the gradient, because what was the gradient? The gradient was the gradient of f was going to be df dx comma df dy as a vector. And so df dx is just taking our function f and taking its partial derivative with respect to x. We did that already. That's 3x squared minus 3. Got another one here. And then the partial derivative of our function with respect to y is right here, 3y squared minus 3. And then we're just, so you don't actually have a new computation for this intermediary step. The only thing that is new is now ddxing this again. Well, what's the partial derivative of 3x squared minus 3 with respect to x? It's 6x. If you go to the lower right-hand entry, what's the partial derivative of 3y squared minus 3 with respect to y? It's 6y. And then, perhaps unsurprisingly for this function, we have zeros down the diagonal here. Because when we dd'd our function, we got 3y squared minus 3. And for this particular function, there were no terms that had both x's and y's. So we have a function that's purely in terms of y. And so when we partial ddx it just becomes 0. Because 3y squared is constant relative to x. Negative 3 is constant relative to x. So its partial derivative with respect to x is 0. Same thing for that other value. Now, you're not guaranteed to have have zeros down the diagonal like this. For this particular function you do. But what you would expect is in this course, for the types of functions that you work with in a multivariable calculus class, you would expect this diagonal to be equal. Even if you don't expect it to be 0, you do expect it to be equal, because derivatives don't really care the order you take them in when we're working with calculus and real numbers like this. So whether you ddy then ddx or ddx then ddy, you would expect the diagonal to give you the same values. Okay, anyway, now we have our Hessian determinant. You just take the determinant of that little 2x2 matrix, and you can see this 36xy. I want you to think of this 36xy as kind of like a tester function. And what I mean, I don't refer to it as a tester function frequently, but this is a good way to frame it in your mind. It is a function that is designed to detect agreement and concavity at critical points. So it's a tester function. You're testing, do the concavities agree with each other in the x and y directions? So we take our 36xy, and we're just going to test each of our critical points. So I'm going to take 1, 1, plug it into my little tester function. I get a positive number, which tells me that I have agreement in my concavities. What are those concavities? Well, either concave up in all directions or concave down in all directions. How do I figure that out? Well, just take this 6x entry and test it at 1, 1, and I get positive 6. And so you could see positive Hessian determinant at 1, 1, positive second derivative with respect to x at 1, 1. I've got a local minimum, and it's that point right there. Now, as we continue through, it's going to be the same for all of these. At least the same step for all of these. So at -1, -1, the Hessian determinant is positive. So we have agreement in our concavities in all directions. The second derivative with respect to x at 1, 1, you take this entry and plug in 1, 1. -6, so our table tells us, our second derivative test tells us local maximum. And then we've got our saddle points. So for either of these saddle points, when you test your point, you get a Hessian determinant that's negative that detected disagreement in our concavities. Saddle point. Same thing for the other one. Negative Hessian determinant. That tells us we have disagreement in our concavities in the x and y direction. Saddle point. All right, so let's move on. Now we're going to talk about the chain rule, which is a very helpful tool to use in this multi-course, particularly in this chapter, but really for the rest of the year. By the way, the chain rule, that should ring a bell from Calc BC. You'll notice a lot of this chapter is really just taking ideas that you're already familiar with from Calc BC and lifting them up to a three-dimensional context. The gradient vector is just a vector interpretation of derivatives. The Hessian determinant is a three-dimensional interpretation of the second derivative test, and we're going to also have a multivariable version of the chain rule. All right, so if we want to get to a multivariable version of the chain rule, we're going to need to build up to it a bit. And what I'd like to do is help you develop some graphical intuition first, and then we can use that graphical intuition to get to the kind of algebraic chain rule that might look more familiar from your Calc BC knowledge. So let's start with just some things that you are somewhat familiar with by this point. For example, I have a surface f of xy. You can see it plotted right there. And then this example says, let x of t, y of t equal some parametric equation. That's a 2D plot that you see right there. And then it looks like we're being asked to put these together. It says plot a parametric path on the surface given by x of t, comma y of t, comma f of x of t, y of t. And I think I can help you unpack this a bit. So first of all, let's make sure we have some good analogies here. So f of xy, I want you to think of that as, it is a surface, but I want you to think of it as a mountain. Maybe you're traveling in Colorado and you're going hiking with your family. F of xy would be your mountain, or in this case it looks more like a valley, but pretend it's a mountain. And then x of t, y of t, this is literally speaking, it's a 2D parametric path. But what I want you to imagine is you go to the National Park Office and you get a map of a hiking trail that you and your family want to hike. When you go get a map from the park office, they give you a two-dimensional representation of the hike you're going on, right? It's going to be a flat piece of paper, a two-dimensional piece of paper representing the hiking trail that you're going to be going on. And then if you're from the Midwest and you go hiking in Colorado, one thing that you realize is what you see on that map is very different than what you actually experience when you go on that hike. If you go hiking in the Chicagoland area, they're pretty much the same, right? You got your map and it's flat, and you go on your walk and your walk is pretty flat. But in Colorado, they're different. Your x of t, y of t, comma f of x of t, y of t is different than what you see on the map because we have altitude. And so it's the actual path that you're walking on that 3D surface living in 3D. It's the actual mountain trail. And there's some difference between the two because you have a change in altitude. Your f of x of t, y of t is changing as you're going on that hike. And you could see that happening in this GIF, right? You're going uphill, and then you're going downhill, and then you're going uphill again. And that's not reflected on this hiking map in the red plot. All right, so let's continue here. So what you can see is like the animations that I made encode a ton of information. And if it was easy to generate these plots, maybe we wouldn't need to use multivariable calculus tools to learn about what's happening on the surface. But this animation took a long time to make. It was a lot of code. And also, you kind of have to watch the GIF looping over and over again to be like, okay, I'm going downhill, and then I'm going uphill, and then I'm going downhill again, so on and so forth. So the animation tells us the direction of parameterization. We could see that this curve is moving in the clockwise direction. We can see when the hiker is going uphill, downhill. But like I said, it's not practical to create an animation like this every single time. So do we have some better tools to figure out what's going on when we're going on this hike? Basically, can we encode some of this information, like the direction of parameterization, when we're going uphill, when we're going downhill, into our 2D plot? So kind of continuing some of the stuff we did in the first part of this lecture, can we encode information about what's happening in 3D on a plot that we can store in two-dimensional space? And we can. I kind of got it ready here. We already invented all of the machinery we need. It's the gradient vector. So what I have here is I've thrown in some extra vectors. So remember we had this point that was moving on that animation, And so we kind of knew our direction of parameterization. We knew that the curve was parameterized in the clockwise direction, but I needed to look at the 3D plot to figure out when was I going uphill, when am I going downhill. So what I did here, like at this point, I threw in an orange tangent vector. That's what this guy is. It's my tangent vector at some particular value t. And then what I also threw in are some blue gradient vectors. So I've got some tangent vectors. Those are great for like figuring out the orientation. I didn't need an animation now to figure out that my particle or my hiker is going in the clockwise direction. And then I threw in some compass readings, some gradient vectors, which is great because it tells us the direction of greatest initial increase on the surface. And now I can learn a lot of information just from this 2D plot. Like suppose you're standing right here. If you're standing right here, so you're a hiker, and we know what direction you're walking in. You're going in this clockwise loop. And we also have this compass reading. We could see that the gradient vector is mostly pointing with the tangent vector. And I could figure that out because I have an acute angle between the two. I could see that the gradient vector is mostly, it's not perfectly aligned with the tangent vector, but it's more pointed with the tangent vector than against. So now you would want to stop and ask yourself, are you walking uphill or downhill at that particular point on your hike? And if you're walking more with the gradient vector than against it, you're walking uphill at that point. This point's interesting because we can see that the direction we're walking in, the orange vector, and the gradient compass reading that we get at that point, they're pointing in almost perfectly opposite directions. So are you walking, again, think about it, are you walking uphill or downhill at that point? And we could see, since this is an obtuse angle, we're walking against the gradient vector at that point. And in fact, we're not just walking against the gradient vector at that point. It almost appears like we're walking against the gradient vector as much as we possibly can. So we're walking downhill at that point. And you might even say that we're walking downhill as steeply as possible at that point. It's like the opposite of the gradient vector. And we have some other ones. So I could pick out a couple more points right here. It almost appears like there's a right angle between the two. So in that case, it seems like we're neither walking uphill nor downhill. We're walking level for a brief moment right there. And then we've got one more right here. It looks like our tangent vector is perfectly aligned with the gradient vector, so we are walking uphill. Technically, there's an acute angle of 0 degrees between the two vectors, but we're not just walking uphill, we're walking uphill as steeply as possible because we're walking with the gradient vector. So you can see these plots encode a lot of information, and you're going to be doing this in your try-it problems, where you're going to be plotting some tangent vectors, some gradient vectors, and you're going to be interpreting what's going on. And so from a two-dimensional plot, we're figuring out what's going on that hiking trail that's on that surface living in 3D. So three-dimensional information from a 2D plot, which is awesome. If you want to put this all together, really what we're doing is we're determining that the angle that's between the gradient vector and the tangent vector is controlling what's going on here, right? I was talking about when the angle between the gradient and tangent vector was acute, obtuse, when it was a right angle. So it's really all about the angle between two vectors. And then you ask yourself, is there some formula that we've been learning about that talks about the angle between two vectors in a meaningful way? And of course there is. And so I would say that the dot product might be a great way to detect angles between two vectors, because the dot product of two vectors is the magnitude of the first times the magnitude of the second times the cosine of the angle in between. So the dot product encodes information about the angle between two vectors. And what we saw, we already walked through, we went on a whole loop around this curve. We saw that when the angle between the gradient vector and the tangent vector was acute, first of all, that dot product would be positive, and we're walking uphill. Similarly, We saw that if the angle between the gradient vector and the tangent vector was obtuse, well, first of all, that dot product would be negative, but that would also tell us that we are walking downhill. And finally, we can use our knowledge of calculus to bring this all together. So remember I just said that when the dot product of the gradient vector and the tangent vector is positive, we're walking uphill on our hiking trail. But walking uphill is the same thing as saying that f of x of t, y of t is increasing. Likewise, I said if the dot product between the gradient vector and the tangent vector is negative, we're walking downhill. And walking downhill is the same thing as saying that f of x of t, y of t is decreasing at t. Now I want to make sure you're sold on that idea. So remember what we had. We had x of t, comma y of t, comma f of x of t, y of t is our hiking trail on our actual surface. Basically, we're walking or hiking this elliptical path, but our altitude is changing as we hike on that trail. Sometimes we're hiking uphill on the hiking trail on the mountain. Sometimes we're going downhill while we're on our hiking trail on the mountain. And so we're trying to figure out those moments when f of x of t, y of t is increasing or when f of x of t, y of t is decreasing. But as calculus students, you guys know what it means for a function of one variable to be increasing or decreasing. F of x of t, y of t is a function of a single variable t. And so walking uphill is the same as saying its derivative with respect to t is positive. df dt is positive. Notice that these are just normal derivative d's here. Or when we're walking downhill, df dt would be negative. And when f of x of t, y of t is decreasing, df dt would be negative. So let's put it all together. Equivalent ideas here. df dt, our change in altitude on our hiking trail, is the same as the dot product between the gradient vector and the tangent vector. And that is our chain rule for multivariable calculus, at least our 2D chain rule. Let's take a look at the next slide and see what we can do with this. So I know this might not look like the chain rule you're familiar with yet, but I'm going to make that connection in a second. The great thing about the 2D chain rule, though, is if you now have a function of three variables, f of x, comma y, comma z, we still have a 3D chain rule. Just add an extra component, a z component in there. We have a 3D chain rule. In fact, we can come up with an n-dimensional or an n-dimensional chain rule for a function of n variables. And in each case, you'll notice it's just the gradient vector dotted with the tangent vector. Gradient dot tangent, gradient dot tangent, which is perfectly analogous to the chain rule you guys know from Calc BC, because remember the gradient is the multivariable analog of the derivative, and then multiplication is analogous to times, and then the tangent vector would be analogous to the derivative of the inside. So remember, you guys had derivative of the outside times derivative of the inside for the chain rule, and that's the same thing here, gradient dot tangent. So you could see if our inside is x of t, y of t, our derivative of the inside is like our tangent vector, x prime, comma y prime, and then the dot product and multiplication are analogous to each other, just one's for vectors and one's for scalars. And then the derivative of the outside, the gradient, is the higher dimensional interpretation of the derivative of a multivariable function. So the gradient of f of xy is like taking the derivative f prime that you're familiar with from single variable calculus. All right, next let's do an example that might be similar to something that you would see on a literacy sheet, on a try-it problem, on a quiz. So this problem gives us an f of xy, a mountain, an x of t, y of t, a hiking trail, or at least a map of a hiking trail, and then we're told to use the 2D chain rule to compute df dt. By the way, df dt, a longer way of writing that would be ddt of f of x of t, y of t. All right, so to use the 2D chain rule, I need the gradient vector and I need the tangent vector. So let's start with the gradient vector. So I'm going to take the gradient of f. This starts out as the gradient of f with respect to x and y. So I'm going to find df dx, partial df dx, and I'm going to find partial df dy. So you take your function, x squared plus xy, its partial derivative with respect to x is 2x plus y. And then the partial derivative with respect to y would just be x. So there's my gradient vector at x comma y. Now, if you look more closely at the chain rule formula, it doesn't have the gradient of f of xy, it has the gradient of f evaluated at x of t, y of t. So I need to take this expression, and I need to plug in my x of t, y of t values in for all the x's and y's here. So this x gets replaced with a cosine, this y gets replaced with a sine, and this x gets replaced with a cosine. This step gets forgotten frequently by students, so I would put a little star right here. Don't forget that step. All right, now let's get the tangent vector. We need gradient of f of x of t, y of t, and I need the tangent vector. Tangent vector is quicker. You just take x prime of t, y prime of t. So you take your cosine comma sine and take the derivative of each component with respect to t. We're good to go. Now, finally, we put it together. The chain rule says that df dt, the thing we're trying to find, is equal to the dot product of that gradient vector we just found and that tangent vector we just found. So plug it all in, smush it together, and then I did notice a trig identity that I could use here. So I do like trig identities. There's actually two trig identities. There's a double angle identity here and a double angle identity there. That would be optional, but it looks really nice at the end, cosine of 2t minus sine of 2t. But you would also get credit if you stopped right there. All right, now that we have the chain rule figured out, we could prove a really cool theorem. The gradient vector is always perpendicular to the level curve passing through its tail. Now, intuitively, you kind of know that this is true, even from the very first lecture from this chapter. We saw a perpendicularity relationship between gradient vectors and level curves, because level curves are what you would walk to stay level. If you don't want to change your altitude, you would walk along a level curve, and a gradient vector points in the direction of greatest initial increase on your surface. And so if you wanted to go uphill as steeply as possible, what you would want to do is get away from a level curve as efficiently as possible. And how would you get away from a curve as efficiently as possible? You'd walk perpendicular to that curve. So we already intuitively know that gradient vectors are perpendicular to the level curve passing through its tail. But with the chain rule, we can prove it, and it's a pretty clean proof. I have seen this on the midterm before. This would be a fair question on a quiz, but let's set up this proof. So suppose we have z equals f of xy, a surface, and a level curve that you would determine by setting f of xy equal to some constant k. And let's say that that level curve can be parameterized as some x of t, y of t. So, imagine that we had one of these level curves and we were able to parameterize it as some x of t, y of t. We could use that to find a tangent vector to our level curve, x prime of t, y prime of t. You can see I'm already getting the pieces of a chain rule here, right? Next thing you could do is you could get your gradient. The gradient of f on that level curve would be gradient of f of x of t, y of t. Now we want those vectors to be perpendicular to each other. That's what we're trying to prove. We want the gradient vector to be perpendicular to the level curve passing through its tail, which would be the same as saying that the tangent vector to our level curve and the gradient vector are perpendicular. We want their dot product to be 0. So let's take their dot product and let's see what happens. So we set up the dot product between the two, crossing our fingers that they eventually work out to 0. Now the 2D chain rule allows us to rewrite that as df dt, df of x of t, y of t dt. That's the 2D chain rule coming in. That's why we're doing this proof now and not before we learned the chain rule. But now let's unpack what this df dt is. Remember that we were walking along a level curve. And so this is ddt of an f of x of t, y of t that was constant. Right? Like that's the idea of walking along a level curve, is that your altitude is not changing. F of x of t, y of t is going to be constant the whole time. So we're taking the derivative of a constant, what is the derivative of a constant? It's 0. Oh my gosh, we just proved it. The dot product of the gradient vector and the tangent vector is 0. The gradient vector is always perpendicular to the level curve passing through its tail. And this is the proof. Probably if you had to do it on a midterm, they'd give you some of this setup information for free. They would be in like the setup to the problem. And then you'd have to do like this stuff and kind of explain the steps along the way. All right, continuing on, in this section, we're going to talk about the directional derivative. So first thing I'd like to do is work through an example that might be similar to something you would see on a quiz or something I know for sure you're going to see on an upcoming try-it problem. So I've got a surface that we've seen before, this x cubed plus y cubed minus 3x minus 3y, plotted right here, a mountain that we might go hiking on. Now suppose that you are standing on this surface at the xy coordinates 0, negative 1 over root 3. So you're standing right here on this surface. And then we're not taking out our gradient compass right now and walking in the direction of the gradient vector. Instead, you have an arbitrary direction you've decided to walk in. Maybe you saw something interesting in some particular direction, and so you decide to walk in the direction of 7, negative 2. And the question we have is, are you going to walk uphill or downhill when you take that first step? And if we look at the plot a little bit differently, if we look at a contour plot right here, we could see I've plotted the direction we're actually going to walk in. I've plotted the point we're standing at. And the other thing I did is I added a gradient compass reading. And by comparing the two, the direction we're actually going to walk in to the direction of the gradient compass, you could tell what's going to happen. The angle between the gradient vector and essentially my tangent vector, the direction I'm going to walk in, is obtuse. And so we're going to walk downhill. We could be a little bit more precise about this. If we're walking in the direction of 7, negative 2, our direction vector is 7, negative 2 divided by the square root of 53. I can also compute my gradient vector at my given point by computing the gradient of f of xy and plugging in the point that we're standing at. This is my gradient compass reading, which you could see right there. And you know what we're doing with this. We're trying to look at the angle between these two vectors, i.e. we should just take the dot product of these two vectors, and this dot product comes out to a negative value, so we know we're going to be walking downhill. It's essentially the chain rule again. This orange vector is like our tangent vector. So it's gradient dot tangent. It comes out to negative. We know we're walking downhill when we take that first step. So this idea of picking a direction to walk in and then getting that direction vector and figuring out if that dot product is positive or negative, it's kind of like I was taking the derivative of f of xy in the direction of 7, negative 2. Am I walking uphill or downhill on my surface when I walk in the direction of 7, negative 2? So what we really did is something called the directional derivative. Now, they might not explicitly say this in your try-it problem, but that's what you were doing. So I can give you a definition here. The directional derivative, if you have any unit vector, then the directional derivative in the direction of that unit vector is the gradient dotted with that unit vector. So it's basically more chain rule. It's just that this unit vector is kind of like our tangent vector. So very much a related concept. The idea of a directional derivative would be if you're standing on your surface at some particular point, there's 360 degrees of directions you could walk in. So in a sense, there's 360 degrees of different slopes that you could have when you take that first step away from that point. And so you kind of have an infinite number of derivatives at that point. Now, the ones we typically work with, you might more frequently work with something aligned with the x-axis or something aligned with the y-axis, or specifically looking at the gradient vector. But there are 360 degrees of directional derivatives at any given point. Doesn't come up a ton, but you might see it. I think it came up on a midterm one year, so U of I asked us to incorporate this idea into our notes so that it's something you're familiar with, and it's something you would see in future calculus courses as well. All right, let's move on here. Let's do some more problems that might help you on triads. All right, so here's a surface, f of xy, and the problem says, show that if we're at the point 1, 1, f of 1, 1, you can see that's that red point right there, and move in the direction of the gradient vector at 1, 1, explain why we have to go uphill on our surface before we go downhill again. This example is in here because it's very similar to something you might see on a triad problem. And I'm going to give you a good way to explain this without having to plot lots of, animated GIFs or complicated 3D plots. So first thing I'm going to do is I'm going to define a parametric path that describes what is in this word problem. So I'm going to define an x of t, y of t equals, so this is a 2D map of our path that we're taking. We're starting at the point 1, 1, because that's what they tell us to do. And then we're moving in the direction of the gradient vector. So we're moving by multiples of this spanning vector, the gradient vector at 1, 1. So I'm going to define that parametric curve. And then in my 3D plot, you can see I plotted this red point. That's where I'm actually standing on my actual surface. So that's the 3D representation of where I'm standing on my mountain. And then we know that we're going to take our first step in the direction of the gradient vector. And so we know our first step is going to be uphill, right? And so we can try to plot our altitude over time by doing the following. So I'm going to try to get a 2D plot of what's going on here. So I'm going to plot f of x of t, y of t versus time. Basically, I'm going to plot my altitude on my hiking trail over time, starting from that point 1, 1. And you can see, this is just a scalar plot here. I didn't write parametric plot. This is just a plot of f of x of t, y of t. It's a scalar altitude plot, and you can see that my altitude is increasing before it decreases again. Now, the more interesting question is, why is it decreasing? Because some students would say, wait a minute, you're following the gradient vector. Shouldn't you always go up? But that's not what the gradient vector at a single point does. The gradient vector tells you that you're walking in the direction of greatest initial increase. Now imagine you're standing on the mountain at this point, and you take out your gradient compass, and you get a direction to walk in. That first step that you're going to take is guaranteed to be uphill as steeply as possible. But what will happen after that is if you put that compass away and you keep walking in that direction, then all bets are off. You might walk uphill again for a little while, but more than likely, eventually, you're probably going to go downhill again. And that's what you're seeing in that plot. All right, let's keep moving on here, just a couple more slides. So we're going to look at gradient vectors and normal vectors. Because remember, gradient vectors are perpendicular to level curves, so maybe we can use gradient vectors to align with finding normal vectors. Let's try it out. All right, so in this example, it says, use your knowledge of gradient vectors to plot some normal vectors to the following circle. So I have a circle here. It's very standard. I could have given you this circle in Algebra 2. That's a circle of radius 2 centered at the point 1, -3. And it says, use gradient vectors to plot normal vectors to that circle. So this is pretty wild, but we can think of this circle as being an intersection between two curves, or two surfaces. So we could think of z equals this guy, and we could think of z equals that guy. And that would be a paraboloid intersecting with a horizontal plane. So in Algebra 2, you would have just thought of this as a circle of radius 2. But now we could think of this equation as a paraboloid living in 3D space and a horizontal plane living in 3D space. And the circle is the intersection, the level curve that we get between the two. And what's cool about that is now that we framed it that way, if we find some gradient vectors whose tails are on that level curve, we just found some normal vectors because gradient vectors are perpendicular to level curves. So anyway, let's do it. So now on this slide, we're actually going to pull this off. So you can see that my animated GIF here keeps switching between just the literal question of find normal vectors to our curve, in this case a circle of radius 2, and then the interpretation where we're thinking of this as a particular level curve in a contour plot and gradient vectors. All right, so here's my f of xy, x minus 1 squared plus y plus 3 quantity squared. That's my paraboloid. The gradient is 2 times x minus 1, comma 2 times y plus 3. Just take partial derivatives here. So partial derivative of this function with respect to x is right here. With respect to y is right there in the y component. And this is just the cool plotting trick. You can use this in Hessian. So to plot some gradient vectors with their tails on our level curve, all we have to do is parameterize our level curve. Well, it was a circle of radius 2 centered at 1 comma negative 3. So there's an x of t, y of t describing our level curve. If we plug that into our gradient vectors, here it is. If we plug in x, and we put for x we put in the x component of this, and for y we put in the y component of this, and you let Hessian plot that, you get these orange vectors. Now I would put a little note here. This should have said x of t, and this y value here I should have written y of t, and then Hessian will just plot these gradient vectors, and those gradient vectors are also normal vectors because they're perpendicular to our level curve. So clever trick for plotting normal vectors. Now I would say in a 2D plot like this, maybe this isn't the most useful trick because we already know about the right-footed normal vector. We already know about the main unit normal vector, that we have plenty of ways of plotting normal vectors. Why would someone spend time using gradient vectors to kind of force some normal vectors? It's for 3D plots, so take a look. All right, and so finally we could put this idea to work. Here's an equation for a surface. It's a sphere of radius 3 living in 3-dimensional space, and we're going to try to find some normal vectors to our sphere. And we don't have something like the right-footed normal vector to use. There isn't just some nice little formula where I write y prime of t comma negative x prime of t and it gives me a bunch of normal vectors. And so in this case, in this 3D context, gradient vectors are very useful. And you'll see this in a triad problem. That's why I'm showing it to you. So we're going to use the same technique. It's a little more mind-blowing now, though, because we're going to write f of xyz equals the left side of our equation for our sphere. And we can't really plot that. I can't write parametric plot 4D x minus 1 squared plus y minus 2 squared plus z squared, because this is a surface living in 4-dimensional space, which is a little bit mind-blowing. But what I can do is I could plot some gradient vectors to this quote-unquote 4-dimensional surface. And so I could take the partial derivatives with respect to x and y and z, and here they are. And I can plot my level surface now. And my level surface, f of xyz equals 9, does live in 3D space. So I've got gradient vectors that live in 3D. I've got a level surface that lives in 3D. It's just my sphere of radius 3. And if I put them together, what do I get? I've got normal vectors to my surface because gradient vectors are perpendicular to level surfaces. So if I reframe my sphere as a level surface, the gradient vectors are going to be perpendicular to it. So this is a really cool method for trying to understand a function f of xyz that lives in 4-dimensional space. So on the one hand, I completed a simple task. I took a sphere living in 3-dimensional space and I found normal vectors to that sphere. So you could think of it that way. Or you could think of this as a way of trying to understand f of xyz living in 4D space via a 3-dimensional context. Because this is a level surface of a 4-dimensional hypersurface, or a hypersurface living in 4-dimensional space. So in any case, I could extract some cool information about 4D space from this plot. So my gradient vectors point in the direction of greatest initial increase on this function f of xyz that I can't even plot. I can't plot f of xyz in four-dimensional space, but I can plot its gradient vectors, and so I know the direction of greatest initial increase on my surface, on my hypersurface. And here's the best way to frame this. I know this is a little mind-boggling, but all you do is you think of f of xyz as a function that tracks a non-spatial parameter. I usually use temperature. So I think of it like this. I'm in three-dimensional space, and I'm kind of swimming in the Fremd swimming pool. And the temperature varies throughout that swimming pool. In some places, the water is warmer. In some places, the water is colder, and f of xyz is tracking that temperature. And perhaps I'm trying to swim in the direction of greatest initial temperature increase while I'm on, say, a point on this level surface. So this level surface would be a place where the temperature, no matter if you swim in 3D space along that level surface, the temperature is always constant. And then if I want to know what direction to swim in for the direction of greatest initial temperature increase in that water, you would just swim in the direction of whatever gradient vector you have at that point. And so you could think of, basically, this plot is showing a bunch of vectors that point in the direction of greatest initial temperature increase on that level surface. All right, and then finally, I just want to point out one more little thing, and then we'll wrap up here. In the triad problems, you're going to sometimes see f of xy, and sometimes you're going to see f of xyz, and I just want to make sure you can distinguish between those two situations. So I've got a nice little table here that should help you do that. So when you have a z equals f of xy, that's a surface living in 3D space, and its level curves live in 2D space, and its gradient vectors live in 2D space. In contrast, if you ever see an f of xyz, technically that's a hypersurface living in 4D space that we can't graph. So you would never see a graph of an f of xyz. Instead, you would want to think of this as having a level surface equal to some constant. That's what you would typically see in a triad. And these gradient vectors are going to be 3D. And so you're going to have gradient vectors that are perpendicular to those level surfaces. And that's the differentiation there. All right, thank you guys so much for tuning in, and good luck on your triads.